Hello everyone, my name is Javier Morlana and I am a PhD student at the University of Zaragoza. Today I'm going to present my work Reduce Your Features, Unifying Image Retrieval and Deep Image Alignment. Our goal is to solve the problem of visual localization. We have a 3D reconstruction of a database of keyframes, which includes a sparse 3D point cloud and the camera poses of the keyframes, which are also known as reference images. The goal is to estimate the camera pose of an unknown image, the query image, with respect to the 3D map. Common pipelines in the visual localization field try to solve this task by splitting it into two different steps. Image retrieval is the first step, where we compress the query image into a compact global descriptor and perform an efficient search of the database, looking for keyframes that observe the same location. Candidates are ranked by similarity, obtaining a subset of keyframes to estimate the pose. The second step estimates the pose for each keyframe candidate in the list, using local feature matching followed by a PMP ransack or deep image alignment techniques. All these methods use multiple networks to solve closely related problems. We believe that it can be solved by a single network. For this purpose, we propose DRAN, a single network able to extract all the features needed in visual localization. DRAN is composed by a unit architecture and uses features for intermediate layers to solve the three tasks of visual localization. DRAN uses an image retrieval pre-trained encoder, able to obtain a compact global descriptor for the image retrieval stage. We use GEM as our global descriptor, which is pre-trained on common image retrieval datasets and requires only image-level labels. The encoder remains frozen, as we do not want to interfere with its retrieval capabilities. Once we have a list of candidates, we continue to the ranking step. DRAN builds hypercolumns from the encoder and the localization head, being able to perform a sparse to dense matching, which re-ranks the list of candidates and gives an initial pose. The sparse to dense matching works in this way. For an image pair composed by a query and a reference, we reproject all the 3D points observed by the reference image, obtaining a set of 2D reprojections. The hypercolumn, which is a set of dense features obtained from intermediate layers of the network, is evaluated at each of the 2D reprojections, obtaining a single descriptor for each of the points. This descriptor is exhaustively searched within the hypercolumn from the query image, obtaining a single match for every point. Once we have a set of matches for each of the pairs in the list, the re-ranking stage ends with a PMP ransack procedure that gives an initial PMP pose better than the coarse retrieval pose. Finally, DRAN performs a featuremetric refinement, minimizing the error in the learned feature space. Starting from the PMP pose, a refined pose is obtained, improving the accuracy of the system. Starting from an initial pose, the featuremetric pose refinement optimizes the final pose by reducing a residual in the feature space. Every 3D point is reprojected and evaluated in both query and reference image, obtaining 2D dimensional vectors. The iterative 11 by Marquardt optimization reduces the residual between these vectors, obtaining a better pose. Our training objective minimizes the reprojection error of the 3D points. For a pair of query and reference images, a pose is estimated. We then reproject the points using the ground truth pose of the query and the one estimated by the previous optimization. The reprojection error between them is the supervision signal to be minimized. Only the decoder and the localization head are trained, while the encoder keeps frozen. We evaluate in three different benchmarks, comparing against other unified and feature matching pipelines. We saw state-of-the-art performance against unified methods, while being competitive against complex pipelines using several networks. The Alation study shows the benefits of the combination of the sparse to dense matching and the featuremetric refinement. Using sparse to dense increases convergence and robustness when initial poses are coarse with respect of the approach of just using featuremetric refinement. Featuremetric boosts the accuracy in final thresholds when the initial poses are given by the sparse to dense matching. We also experimented with a light version of DRAN and compared against a hierarchical approach that uses 3 individual networks. DRAN performs similarly to it while being cheaper and faster, showing the potential to be further miniaturized to extract all the features needed in a SLAM pipeline. The benefits of the combination of the sparse to dense and the featuremetric approaches are shown here. On the left, we use the coarse retrieval pose as initialization, resulting in a failure for the photometric optimization. On the right, we initialize with the sparse to dense pose, obtaining a much better initial pose that the photometric optimization can further refine. DRAN is able to match images in day-night conditions, overcoming occlusions and viewpoint changes, and also works well with seasonal changes in driving scenarios. In this paper, we have shown the DRAN, a single network able to obtain all the features needed for visual localization. We see DRAN as a first step towards a unique feature structure for visual localization and SLAM. Thanks for listening. Please check out our GitHub if you want to know more.